Hello again. Here we are with our continued part of Case 3, Complex Conjugate Roots, still in section 2.2, still to remain there for a little bit longer as yet another recap, right? We have our general second order ODE, constant coefficient, homogeneous, written this way, and we had always been writing A, B, and C are real numbers, and now you kind of maybe see why, it's important to say that A, B, and C are real, because here we end up with a case where we get these complex conjugates roots, which lead to solutions that involve complex variables, okay? So we looked at an example, and we didn't go any further than this. And then we took a nice, fun foray through the exciting adventures, just got a tiny little peek into some work with complex numbers and understanding I and complex conjugates. And so now we're going to kind of veer back on the path to why it's important, what piece of that we want to focus on, and why it's important to us, right? So that's where we are. We're pulling ourselves back now out of that world and back into, okay, what piece of it do we want to focus on? So remember, when we have a characteristic equation, quadratic, for a second order constant coefficient, we've got three possibilities that could come out of that. Either two distinct real roots, a single repeated root, or complex conjugate roots. And so we always have two roots, right? And it's just, they're different, they have a different character. And so in this case, right, what does that give us? I'm not even going to call them y's, right? This gives us, I'm going to call them, this is a brand new marker and it does not write real well, right? Okay, not so good. This gives us two complex valued solutions. Okay, and I'm going to call them Z1 of x, right? So what would Z1 of x be? Well, it would be e to the R1x, right? And what would R1 be? E to the alpha plus I beta x, right? So that's our R1. What's our R2? That gives rise to our Z2, e to the alpha minus I beta x, right? In general, okay? And we had written down those two solutions for alpha being half and alpha 3/2 for this problem, but we said, hey, wait a minute, we started with everything real. We want y to be a real valued function, and now we're getting solutions of this differential equation, which are totally legitimate solutions, but they're complex valued functions. What you put in, you get out a complex valued result. And so the question becomes, can we get real valued solutions? Right? And in fact, two, which are linearly independent. That's our goal, right? Okay. Well, let's think about these two guys, right? Z1 of x, right? So, and Z2 of x. In general, e to the alpha plus I beta x, e to the alpha minus I beta x, right? Okay, well, let's just work with this one for a sec. So, distributive law, e to the alpha x plus I beta x. Right? Distribute x across, right? Okay, rules of exponents. How can I rewrite e to the alpha x plus I beta x? Rules of exponents, Yeah. Good. Right? E to the alpha x, good, times e to the I beta x, right? Good. Okay, What can you tell me about that part, e to the alpha x? What can you tell me? Yeah, I think I heard somebody say it's positive. Yes, you're right. That is super true. We're really good at that now. But in the context of this, we want to get real valued solutions. What can you tell me about e to the alpha x? Good, 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 right? This is real, okay? This is real value, right? Because alpha is a real number, right? The real part of one of the complex conjugate solutions, the real part, alpha, is a real number, right? And so this is just e to a real number times x. That is real valued. This part is complex valued. Because there's our I, right? And then what about this one? Pretty much the exact same thing. We'll skip the middle step. This is e to the alpha x times e to the minus I beta x, right? This part is real. This part is complex. So, these two guys are our solutions, our complex valued solutions. We could write them each this way. They each have this real part, right? So, okay, we want real valued solutions. So can we just take the real valued part? Let's just call e to the alpha x the solution and be on our way. And what do you think? Just call it e to the alpha x a solution and then use reduction of order to get another solution. Good, good, good. No, we can't do that, right? Why can't we do that? Because e to the alpha x is not a solution to that differential equation. How do we know that? Alpha itself is not a root of this characteristic polynomial. So since it's not a root, the e to the alpha x is not going to satisfy this differential equation all by itself, right? So you can't just ignore the complex piece. You have to deal with it, right? Oh, that's a statement if we've ever heard one, right? You can't just ignore the complex piece. You have to deal with it, right? That's some good life advice. Anyway, here we go, right? So we know this piece is real valued, so let's try to focus on that other piece, right? So let's focus on this, okay? So let's focus on these pieces. The complex pieces, right? Okay, so I'm going to leave our little example sitting here. I probably ought to leave it there, okay? We'll come back to that at the end. All right, so we're going to focus on the complex part. Let's look more closely at the complex part. So what's the complex part? Well, it's e to the I beta x for that, the one solution that comes from one of the roots, and e to the minus I beta x for the solution that comes from the complex conjugate root, right? They both have the same kind of form. E to the I times thing, right? E to the I times thing, okay? So let's look instead. E to the I times theta. Let's just call it theta. So for this guy, theta is beta times x, and for this guy, it's minus beta times x, right? Okay? All right. So let's see if we can come up with some other way to write this. E to a thing. E to a thing. So this guy's a complex exponential. E e to a thing. All right, what's another way? Let's rack our brains. Rack. Our brains. Or wreck our brains, maybe, right? Let's rack our brains with our Calc 2 knowledge. You know, when you're kind of stuck with stuff that you aren't sure really what to do with, by the end of Calc 2, what do you do? Cry? Okay, yeah, you're right. But by the end of Calc 2, what have you become very accustomed to doing? Yeah, right? Rewriting a function in this nice explicit form instead. How? As in, you got it, infinite series, right? You're super excited? You're super, super excited. So let's recall from Calc 2. Let's go to e to the x, right? Can you rattle me off the infinite series for e to the x? Power series for e to the x, the Taylor series expanded about x equals 0 for e to the x, right? What do we have? We've got the sum, k equals 0 to infinity of x to the k over k factorial, right? Let's write it out. It's nice and concise with our summation notation, right? Okay. What would it be when k is 0, right? We've got x to the 0 over 0 factorial. Sum means add. Increment the counter by 1. K equals 1. That's x to the 1 over 1 factorial. Sum means add. Increment the counter by 1, right? X squared over 2 factorial, right? Plus x cubed over 3 factorial, right? Plus x to the 4th. You get this? Yeah? Making sense? What's the next term? Good. X to the 6 over 6 factorial. Keep going. Look, we have more board. Yeah? When is this going to end? When is it going to end? When am I going to be able to stop writing terms? Right? Never! Right? It goes on forever, right? Forever. Yeah? Okay. And what do we know about this guy, right? What is the interval of convergence for this Taylor series? Maclaurin series, really? Good, minus infinity to infinity, right? It has an infinite radius of convergence, right? So as long as we take infinitely many terms, this sum is exactly equal to this guy, yeah? Okay, well let's just keep going here and making sure we know what these things are. So just to make my life simpler, what is x to the 0 power? 1, okay. What is 0 factorial? 1, nice. So 1 over 1 is good. 1, okay. So what do we have here? X to the 1 is just x, right? Divided by what's 1 factorial, also 1, right? And so usually you'll really see it more like that, yeah? Okay, nice. And so what does this mean, right? This means the same thing as saying x is any real number, right? As long as x is any real number, we have this infinite power series representation, right? Okay. Well, let's get a little wild and crazy, okay? Right? Yeah, I've been doing online class for forever. A little wild and crazy isn't so bad. So what do we got? This is true, we know, for any x, any real number. But, you know, like the exponential function is pretty crazy, and calculus is pretty awesome. What if we took a giant leap of faith to assume that it's also okay if we put in complex things over there? Yeah? Well, that would be super cool, right? And if you want to study more complex variables, take Math 360. Okay, so let's do that, okay? Let's take a leap. And say, what about e to the I theta? Okay, in fact, I'm actually going to take my leap up just so that I have more room. Okay, so you already know that. Let's take a leap. So let's leap up here. Yeah? Okay, so if we then want to evaluate e to the x at I theta, well, this guy would say, how would we do that? Well, we put an I theta everywhere there was an x, right? Okay, so what do we got? We got 1 plus I theta plus I theta squared over 2 factorial, right? Plus I theta cubed over 3 factorial plus, right, I theta to the 4th over 4. Yeah, you getting that? Right? Okay, that's how you evaluated, you know, e to stuff with an infinite series in the end of Calc 2. You could put anything there, you just put it wherever x is, right? No, we're taking a little bit of a leap because you could put anything real there, and I theta isn't always real, right? So, anyway, all right, let's keep going. Write a few of these guys. Yeah, a few more, you're getting it now, right? Okay. Yeah? So we know where that came from. Yes? Awesome. Okay, well, let's keep going. I'll leave this here for just one more sec so you don't. Well, let's, you know, do some math with exponents, right? So we got 1 plus I times theta plus I theta squared is I squared theta squared, right? Yeah? Plus I theta cubed is I cubed theta cubed. Yeah? I to the 4th, theta to the 4th. I'm hearing you get excited. Yeah? Oh, what did we do last video? Last class, I would have said, normal times, right? Okay, yeah, let's write out a few more. I to the 7th, theta to the 7th. I to the 8th, theta to the 8th. Right, the next term will be I to the 9th, theta to the 9th, and then we are going to run out of word space, so we'll say dot, 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 right? Okay, continuing with our leap, right? Now, what did we remember? So let's write this over here, right? Let's recall. Last time, what did we do? Well, we said we went through this idea. We had I, right? And then I squared, we know is -1, right? That's the whole idea, right? We talked a lot of different ways to understand this idea, right? Writing I squared equals -1 has so much in it, right? Geometrically, algebraically, in lots of different ways, okay? And hopefully that gives us more understanding of writing I as the square root of -1. It really means much more than just the notation, right? Then I cubed, right, is minus I, because we're multiplying that guy by I, and I to the 4th is good 1, I squared times I squared is 1, and then I to the 5th is what? Then this cycle just continues again. I, -1, -I1, right? So I to the 6th is -1, I to the 7th is -I to the 8th is 1, and the cycle continues, yes? Awesome. Alrighty. So, what do we got here then? We have got, all right, 1 plus I theta, I squared. What am I going to replace I squared with? I squared is -1. So this is going to be minus theta squared. Yeah? Okay. Plus, okay, too many things in my hand. Can't hold caps, markers, and erasers. All right. So then, plus I cubed is minus I, right? Minus I, right? Plus I to the 4th is 1, right? 1 times theta to the 4th, yeah? Plus I to the 5th is I. I'll just put it there so that we can see it, right? I'll make this I blue too, just so you see it. Okay, and plus I to the 6th is -1, so we're just going to have a minus there, yeah? plus I to the 7th is negative I. Yeah, plus I to the 8th is 1, right? So I to the 8th becomes 1. And then we just keep going all over. So what is I to the 9th? Good, back to I, right? Yeah, makes sense? Are we all good there? Okay, awesome. Alrighty, so now what, right? So what would actually be the sign right here? I to the 10th, right? It's gonna be a negative, right? Yeah, right? Okay, good, yeah. Awesome, right? I, negative 1, okay. So here we are. Well, at least there's less messiness, right? All right, something simplified. Well, what do you do with complex things, you know? What do? You put like the real part, and then you look at the imaginary part. The imaginary part is the stuff that goes with I. So let's do that with this crazy function here, this infinite series, yeah? Okay? So now, let's gather the real part of this expression. That will be everything that doesn't multiply in I. So what do we got? 1 minus theta squared over 2 factorial. Skip this guy, he's got an I, right? Skip that guy, got an I, right? Every other one's going to have an I. So plus theta to the 4th over 4 factorial. See it? Minus theta to the 6 over 6 factorial. Getting excited? Okay. Right, one more. Plus theta to the 8 over 8 factorial, right? Minus dot 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 on and on forever, right? Theta to the 10th over 10 factorial, yeah? And we keep going with all even powers of theta here, yeah? Yeah, yeah? All right, then what are we gonna do? Plus, right? Now I is gonna multiply all the rest of this, so I times what's left, right? And so again, remember how I said sometimes you put the number in front, like, and sometimes you put the I in front. When it's a number, it's usually the numbers in front. When it's not, it's back here. Okay. Anyway, so let's keep going. So now I'm going to go back and pick up everything that had an I in it. What had an I in it? Theta. All we're doing is rewriting this algebraically correct. Then what else, right? Then we already factored out the I, so now we have a minus theta cubed over 3 factorial. You getting excited here? Then we have a what? Plus theta to the 5th over 5 factorial, yeah? Then what? Minus theta to the 7th over 7 factorial, right? We already factored out the I, right? Last one, plus theta to the 9th over 9 factorial, yeah? What would the next term be? Good. Minus theta to the 11th over 11 factorial. Let's just write it for fun. Yeah? Then plus, on and on and on, where all of these guys have odd powers, odd factorials. Yes? Yes, yes? What do you see there? Just for fun, right? Let's refresh. Writing this guy as an infinite series with summation notation, this would be the sum k equals 0 to infinity of what? Well, I've got even powers of theta, so theta to the 2k is even, right? Start at k equals 0, theta to the 0 is going to give me 1, right? Divided by, well, I need that number to be the number factorial, right? So that's the quantity 2k factorial, even number factorials, right? Yeah? That's what that is. When k is 1, I get theta squared. Oh, that's not what that is. Hold on, right? It's good that we did that. We had to count for alternating sign, right? So we need minus 1, either to the k or the k plus 1, okay? Theta to the 2k. All right, so when k is 0, we want it to be positive, so k. So when k is 0, it's positive, so when k is 1, right? Then we're going to get minus 1 to the 1, so we'll get our negative theta squared over 2 factorial, right? When k is 2, what are we going to get? Minus 1 squared, right? That's going to give us our positive. When k is 2, theta to the 4th over 4 factorial, right? Okay? So that's that piece. Plus I times, what do we have over here? This part right here, well, maybe I'll just, like, so that's all. Just kind of to emphasize how nice the summation notation is, right? It's a lot. We've written out every infinitely many term here. Here we only wrote out 1, 2, 3, 4, 5 terms, right? Took up so much space, right? Okay, anyway, plus I times, what is all of this the same as? Summation. Let's write it as a sum. I know what you want to say. You're not going to say it just yet. Sum k equals 0 to infinity of, again, we're going to need some alternating sign. Our first term is positive, so minus 1 to the k would accommodate that, right? And then what do we have? We need odd powers. How do we create an odd number? Good. 2k plus 1, even plus 1, right? Okay, all divided by 2k plus 1 factorial, the even number, right? So if k is 0, I get theta to the 0 plus 1, so that's my theta. I get a 1 there, 1 factorial is 1, we're good. And when k is 1, I'll get my minus sign. This is theta cubed over 3 factorial, and the whole thing keeps on going, right? When k is 2, I'll get my positive, and then this is theta to the 5th over 5 factorial. So there we are, okay? So that is the infinite series way of writing e to the I theta, right? And you've been waiting and waiting to tell me what is that, this or that. What is that equivalent to from calculus? Beautiful. This is cosine of theta, right? Cosine of theta. This is the Maclaurin series for cosine of theta, which is valid for all theta, right? Theta, any real number, right? And here theta is a real number, right? Because theta was representing, I have it erased, beta x or minus beta x, right? Beta x or minus beta x. Theta is real, right? Okay, beta was real, x was real, minus was real. Okay, so that's this guy, so this equality doesn't even require a leap. And then, what is this guy? Awesome, this guy is sine theta, right? Again, this is the Maclaurin series for sine theta, which is valid from minus infinity to infinity, right? And so we get this magical formula. What did we just discover? Here it is. E to the I theta is cosine theta plus I sine theta. This is Euler's formula, 1748, I believe. Boom, there it is. Expo marker drop. That's crazy. All right, so I'm gonna erase this, let you gaze at the formula, and now you know where it came from. It required our one little leap up there, which is legit and true. This math is so cool and amazing. Maybe that'll inspire you to take complex variables. Okay. Now, this is still a complex value thing, right? The real part of this function is cosine theta. The imaginary part is sine theta, both real things. And e to the I theta is just cosine theta plus I sine theta. Yeah? Okay? All right. So what do we know? E to the I beta x, then, which is why we started going to this idea, is what? What is theta? Theta is beta x, right? So e to the I beta x is cosine of beta x plus I sine of beta x. Beta is a real number, right? Where did beta come from? It came from those roots, right? It's the imaginary part of the complex conjugate root. And if theta is minus beta x, e to the minus I beta x, that's the same as e to the I times minus beta x, right? Yeah, so theta's, then what do we know? That's cosine of minus beta x plus I sine of minus beta x, right? Because you're putting a minus beta where you see a theta, yeah? And those were the two pieces that were causing us trouble. So let's write that down again so you remember where that came from. So recall, our complex valued solutions are z1 of x, which was e to the alpha x, e to the I beta x, and z2 of x, which is e to the alpha x, e to the minus I beta x, right? Where alpha is the real part of the complex conjugate root, and beta is the imaginary part of the complex conjugate root, right? So for this problem, that guy is alpha, and that guy is beta. We'll come back to this right now. But these guys are still complex. Now we can, what do? We found that we can replace that part with these guys, right? But these guys are still a little bit ugly, right? And still complex, right? So let's rewrite this one. So what do we have? We've got e to the alpha x times, so at least it's not complex up in the exponential anymore, right? We can rewrite this complex exponential how? Cosine beta x plus I sine beta x, right? Because of that. Now, before we dive in and plug that guy in, what do you remember about this? So if we evaluate negative beta x, right? Then what do you remember about cosine? Remember how the power series only had even powers, right? I mean, cosine is an even function. What's true about an even function, right? An even function, cosine of minus beta x is going to be the same as, I hear it, cosine of beta x, right? It doesn't matter which side you're on to evaluate, you get the exact same value out of cosine, right? Okay, awesome. Because cosine is even, tell me about sine. Sine is odd, right? And had odd powers only in its Maclaurin series. So what do you know about an odd function? Sine of minus beta x is good, minus sine of beta x. So the minus comes out. Yeah? So if I'm at the origin and I go equal distance away, right? If I do this guy, right, evaluate here, and that's going to be doing the same as down here, right? Does that make sense? Sine of minus beta x is minus the sine of beta x. Yes? Okay? All right. So we're good. We've got this guy simplified, right? And so let's put that in here. Our second, these are still complex valued solutions though, right? We still have complex, so we still have some more work to do, guys. So what do we get though? We get cosine of beta x, but minus I sine beta x. Okay, so now the nice thing is 1978 and still giving good info, right? Sorry, 1748 and still, right, has not become obsolete, right? Yeah, not much from 1748 is not obsolete. Yeah, you gotta love math. All right, so many more things we could talk about with this formula as well, but we gotta make these videos end, right? Okay, so now we at least have another expression that let's write these guys out. At least it doesn't have the complex up in the exponential, but we have it written out more. So let's write this out, multiply through the e to the alpha x. So we've got e to the alpha x cosine beta x. That's the real part of this solution. That is a real function. Plus, distribute the e to the alpha x I times e to the alpha x sine beta x, right? E to the alpha x sine beta x is the imaginary part, right? That's a real valued function, but it's multiplied by I, and that makes this function complex, right? And this one, z2, is e to the alpha x cosine beta x, right? And then what? It's just minus I e to the alpha x sine beta x, okay? So, we still have complex value solutions. They're not quite as short as they used to be, but they're in better shape than they used to be. And let's see why, okay? Notice, right? So the real part of z1 of x is e to the alpha x cosine beta x. And that's also the real part of z2 of x, right? Yeah? So that guy let's just call that something shorter to write. All of that is a lot to write. Let's just call it u. Let's call u of x e to the alpha x cosine beta x. Okay? All right. Now, similarly, the imaginary part of z1 is e to the alpha x sine beta x, and the imaginary part of z2 is minus e to the alpha x sine beta x. But e to the alpha x sine beta x seems like another kind of function that's a real valued function that we ought to at least call something else. So let's call v of x e to the alpha x sine beta x, right? Now, plus it, minus it, we've kind of learned the differential equations, right? If we multiply stuff by constants, we're in pretty good shape. So let's just go with this nice, simpler, easier piece. Now, these two guys are real valued functions, right? Alpha is a real number, real part of the complex conjugate root. Beta is a real number, the imaginary part of the complex conjugate root. So these two guys are real valued functions. Huh. I wonder if there's any way, right? These guys are complex valued functions, and they're solutions of our original differential equation. But do you think there's any way that those two pieces that show up in the complex valued solution could possibly be solutions of the original differential equation? Because that would be super cool if they were, because then we'd have two solutions. And then if we could show they're linearly independent, we would have two real valued solutions, and since we're in second order problems, we're now golden. Does that make sense? Are you getting excited? Now, how are we gonna do that without writing 1,000 things out again? Okay, so here we go. So now we're taking our complex value solutions and being like, hey, what if we look at each piece separately? Okay, so let's think about Z1 itself, which I just erased, but it's right here. Right? With our new definitions, right, what is Z1? U of x plus I times V of x, right? And what is Z2? Z2 is U of x minus I times V of x. Yeah? Z1 is U of x plus I times V of x, right? Now what do we know? We know Z1 of x satisfies our ODE. What was the ODE? A y double prime plus b y prime plus c y is equal to 0, right? So what does that mean? If I put a z1 everywhere there's a y, that will be 0, right? Okay? So if I don't want to have to keep writing all of this stuff, I could just call this, use operator notation and say this is L of y. So what does L mean, right? L at itself as an operator is a constant times the second derivative with respect to x plus another constant times the first derivative with respect to x plus another constant. And that's this little operator that's out there waiting to attach to something. And if L attaches to y, then what happens, right? Y gets the constant A multiplied times the derivative, right? So if I do L, right? So then if I do L of y, what does that mean? I'm putting a y here in these spots, right? And that gives me this, right? That's what's happening, yeah? Okay, and so it's going to be simpler for us, we've already talked about operator notation, to think of it that way. So what do we know? Since we know Z1 satisfies our ODE, what do we know? We know that what is L of Z1 of x equal to? 0, right? We know that L of Z1 is 0 because Z1 is a solution. It's a complex valued solution, right? Okay? Complex valued solution, yeah? L times Z1 double prime plus, or sorry, A times Z1 double prime plus B times Z1 prime plus C times Z1 has to be 0. That's what this says right here, right? Okay, but let's explore this L of Z1. Given that we just said, well, we're going to let Z1 be U of x plus I times V of x, yeah? Okay? Well, we've already looked at adding two functions together and multiplying a function by a constant, and when you do that with constant coefficient or even linear, right? In linear, that's where it's going to be even more important to us later, but linear constant coefficient ODEs, then if I plot U, what does this mean? I'll just kind of write it right here, right now. This means A times U plus, I'll write U of x. U of x plus I times V of x double prime plus B times U of x plus I times V of x prime plus C times U of x plus I times V of x itself, right? That's really what this means, right? Because that's what L does, right? Puts whatever is here in these spots and does that, yeah? But we want to get away from that. We've done that an awful lot and get to the fact that if we do this and utilize the properties of derivatives and, trust that the properties of derivatives hold when the constant is a complex valued constant and not just a real valued constant, then what we will get is A times U of x, U double prime of x, plus from here, plus B times U prime of x from there, plus C times U of x, okay? Plus if I pull out the I times a B double prime of x, I pulled out, plus B times B prime of x, right? Because the prime goes to each guy, I is a multiplying constant, complex constant, but the same. Plus, pull out the I, which is out there, C times V of x, right? So you can go through the steps to get there if that was too fast for you, okay? But let's write this in operator notation. This is, right, plugging piece right there, there's a v, right, where there's a y. I times L of v. Yeah? U of x, v of x. Well, we're pretty close now, okay? What did we originally say since z1 is a solution? What did we originally say L of z1 has to be? It has to be 0, right? So what do I know? That this guy is 0. But what is 0 for complex numbers, right? Remember, this is complex. What is 0 for complex numbers, right? It's 0 plus 0i, right? 0 is the same as 0 plus 0i for a complex number, yeah? So this has to be true. Now, what did we say about two complex numbers being equal? If two complex numbers are equal, the only way this can hold is if and only if what's true. 0 plus 0i is equal to this plus that I. Well, the real parts have to be the same. L of u is 0. And the imaginary parts have to be the same. The imaginary part is 0. The imaginary part is L of v, right? Right? It's the only way that's possible. And we know that had to be true because we knew z1 was the solution. Well, what does this mean then? This means u solves the ODE. If L of u is 0, that means a times u double prime plus b times u prime plus c times u has to be 0. So this real valued function is a solution. And what does this mean? V solves the ODE, right? So what does that mean? This real valued function is another solution. And they're real valued. So we have two real valued solutions to the differential equation. Oh, so exciting, right? And talk about the principle of superposition and linearity of an operator, be able to go straight from here down to there. Okay, you go straight from there down to there. L of u plus IV is L of u plus I, L of v. And distribute across the sum and pull out a constant, okay? So our truth about complex numbers and equality of complex numbers then gives us that each one of those real valued pieces have to be solutions. We don't have to check if they are. Have fun checking it if you want. Right? Product rules, second derivatives. And so now what is left to show? So provided u of x and v of x are linearly independent, that's the other piece left. Provided u of x and v of x are linearly independent, then the general solution to our ODE in case 3 is y is c1 y1, which our y1 is u, e to the alpha x cosine of beta x, plus c2 y2, what is our y2? V, very nice, e to the alpha x sine beta x. Woo-hoo! Yeah, we worked hard for that, but that was super cool and awesome, right? So let's come over to our problem that our example problem we were working on last time. Last time all we had was the complex valued solutions, and now that we know this, we can immediately write down the general solution, right? After we go and show that we have linear independence, which you're gonna do in just a sec. But what would be the solution to this equation then? Y is, what is alpha? 1/2. What is beta? 3/2. So y is C1 e to the 1/2 x cosine 3/2 x plus C2 e to the 1/2 x sine 3/2 x. And that is our solution of our example problem, general solution of our example problem we did last time. Notice there's no i's in our solution. It's not plus ci, right? Okay, we just went through all of that work to not have an I in our solution so that we have a real valued solution, right? Why am I saying that? Because students constantly leave the i's in, right? That's just wrong. We want real value, right? We just went through all of that to say we don't have any i's in the general solution, right? It's not complex valued, it's real valued. And this is going to represent all possible solutions, so we're not leaving anything out. That is crazy. All right, what's left? Show these two guys are linearly independent. Yeah? Okay, you ready? Whew. Need some water. You should get a drink of water too. Let's see. Make sure I don't forget to say anything that I wanted to say. Okay. Alrighty. So, linear independence. Are they linearly independent? Well, what does that mean, right? We look at a linear combination of them, so C1 e to the alpha x cosine beta x plus C2 e to the alpha x sine beta x. Set the linear combination equal to what? 0, and ask, is C1 equals C2 equals 0 the only solution to that equation, right? Now, this is the more general way of talking about linear independence, right? Because it's only two functions, there are easier ways to talk about linear independence. And the other question, or we can ask, is U of, let's just say, is R, U of X, and V of X, constant multiples of each other. That's another way. Okay? So, it's up to you, how you want to do that. This idea generalizes to three and 4 and 5 and 6 and n dimensions, which is where we're going to go. Let's look at this equation for a sec. If we were going to try to think about this, there's a variety of different ways we can think about it. Now, since we do know e to the alpha x is strictly positive, right, we could divide the equation by e to the alpha x, and that just gives us a simpler equation, C1 cosine beta x plus C2 sine beta x, right? And it's equal to 0. And so there's a variety of things you could do. You could plug in values for x, right? Like x equals 0, x equals pi over 2 beta, something like that. Easy values. that can easily give you C1 equals C2 equals 0. You can solve for one in terms of the other, right? So if you bring this guy across, you would have a minus there, right? And then if you divide by, sine, when sine is not 0, divide by C1, right? You could say, okay, well, this is a constant, this is not constant, right? So that's not possible, so therefore we can't do this unless C1 and C2 are 0. There are a lot of ways of here in the constant multiple version, you can be like, okay, your sine of beta x, right? So cosine is not, we would have e to the alpha x in there as well. Okay, sorry. So again, same deal, right? That we don't have the ability to say that we have this equation holding for all x real, right? For two constants C1 and C2 unless C1 and C2 is 0, okay? So you can look at that yourselves in a variety of different ways. We're going to also learn about another thing that will allow us to systematically talk about this idea as well and generalize it, but it's a little more complicated than just reasoning through, okay, when we have this over here, this side is not constant, this side is constant, and therefore there's no way that can be true, or that we can't have a single constant for all real numbers x, okay? By plugging, same deal as plugging in two different values for x, getting two equations that force you to make C1 and C2 0. Okay, final comments. So the answer is yes, those guys are linearly independent. In the process, you kind of show cosine beta x and sine beta x are also linearly independent. So that's a nice little sidebar there. Suppose we had an initial value problem for this guy. Let's look at that and close it up with that. What if we had an initial value problem? Right? Okay. Let's just make it relatively simple. Y at 0 is 5. Y prime at 0 is 3. So what would you do? You would have solved this guy the exact same way. Okay. Come up with our general solution. Which is this. Then you got to apply those two conditions, right? Now for this one, since I'm assigning it at 0, that's going to make things relatively simpler, right? So what is y at 0? If I evaluate this function at 0, what am I going to get? C1 e to the 0. E to the 0 is 1 times cosine of 0. What's cosine of 0? Good, 1 plus C2 e to the 0, which is 1, times sine of 0, which is 0, right? Okay, so what is y evaluated at 0 for that function? It's just C1. So the initial condition is awesome. We get 5, right? For the first guy. So then what would I know? Okay, well I can put in 5 for C1. So what is y as a function of x? It's 5 e to the 1/2 x cosine 3/2 x plus C2, which we don't know yet, e to the 1/2 x sine 3/2 x. Yeah? Now you're going to do y prime, right? And so while we often write it this way, when we're writing down the solution, if you're going to do y prime, since that's the same function, it's actually simpler to rewrite y of x, right? To factor out that e to the 1/2 x, right? The e to the alpha x before you do the y prime. So we got that guy. Then what are we left with? 5 cosine 3/2 x plus C2 sine 3/2 x. Yeah? I know this video is running long. but, and I'm running out of steam too, but I just want this to end. I mean, I just want to be able to finish this out for you, and I want this to end. I know you want it to end. All right, okay, so this is the same thing, right? But if you write it this way, then to take the derivative, you just have one product rule, and if you leave it this way, you got two product rules, right? Okay, and so let's just do y prime, just to make sure we're all there. So what's y prime? First guy times the derivative of the second guy. So what do we got? Derivative cosine is minus sine, right? I'm going to get minus 5 out there. Then I'm going to get sine 3/2 x. But then I got to multiply by the derivative of what's inside. So instead of 5, I'm going to have minus 15/2, right? Yeah. Okay. Plus, what's the derivative of sine? Cosine c2, right? Cosine of stuff times the derivative of the stuff, right? So that's going to be plus 3/2 c2 cosine. Yes? So that's the first times the derivative of the second. Yeah? Plus the derivative of the first. What's the derivative of the first? E to the stuff times the derivative of the stuff, right? Times the second. What's the second? 5 cosine 3/2 x plus c2 sine 3/2 x. Woo! Right? That's a lot. Okay, we're super close. Look how messy my hands are. All right, now we're gonna do what? Evaluate y prime at 0. So what is y prime evaluated at 0? Well, this piece is e to the 0, which is 1, right? So it's nice that it's evaluated at 0, right? If this hadn't been evaluated at 0, all of it was gonna be such a mess. Sine of 0 is 0, right? So that's gone. So then we're gonna have cosine of 0 is 1. So we're just gonna have 3/2 c2 come out of that top piece, yeah? Okay? Plus 1/2 e to the 0 is 0. 5 cosine of 0 is 1, so we're going to get times 5, right? Plus c2 times sine of 0 is 0, right? And so nothing else comes out of that, yeah? All right, so what do we get? 3/2 c2 plus 5/2, and what do we want y prime to be? 3, right? So if I'm going to solve that, I'm just going to solve that through c2 multiplied by 2. 3c2 plus 5 is 6, right? 3c2 is, can we do this arithmetic at this point? I don't know, I think we're all, punch drunk here. Minus 5 is 1. C2 is 1/3. Lo and behold, then what would be our solution, the unique solution to our initial value problem? We're going to still have yet to kind of justify that coming up. Unique solution to our initial value problem would be right here with these choices of the constants. Woo! We did it! Yeah! All right, it's weekend for us, for sure.